Welcome back. Today we will discuss the two more complicated operations when dealing with mixed numbers, and that is the operation of multiplication and or division of mixed numbers. Last time, we saw that there were a number of ways that one could, say, add 3/2 with 5 and 1/4. On the one hand, we could represent, say, the addition or perhaps the subtraction of 3/2 and 5/4 using a more algebraic notation. We could convert, say, this 3 and 1/2 to its algebraic form, 3 plus 1/2. And we could, say, convert this 5 and 1/4 to literally 5 and 1/4. And if we did that, then using the rules of algebra, you could first say remove your parentheses and then do rearrangement via the commutative law. You would then be able to add your whole numbers and then address, say, the fraction components of your mixed number, in this instance by, say, using the LCM, the least common multiple, in order to locate the common denominator, which in this instance would be 4. So you would say multiply this 1/2 by 2/2. And if you did that, 2 times 1 gives you 2, 2 times 2 gives you 4. So you'd have 2/4 plus 1/4 plus 8, which gives you 3/4 plus 8, which is literally 8 and 3/4. We said that in addition to this method, though, you could also say simply add the whole number components, which would be 3 and 5, which giving you 8. And then as long as you say did a little bit of a conversion to that 1/2, maybe you multiplied on the top and the bottom by 2. So you would take, say, 2/4 and then add it with 1/4, you would then get 3/4. Okay. And that would be another way of perhaps more quickly being able to add 3/2 and 5/4 together. We also saw a third method of being able to add 3/2 and 5/4, and with this was simply we should convert back to an improper fraction from the mixed number by first taking your denominator, multiplying it by the whole number. 2 times 3 gives you 6, and then adding it with the numerator, which in this instance is 1. So 6 plus 1 gives you 7. So the improper fraction representing 3 and 1/2 would be 7/2. And then you could do the same thing here. You could take 4 and multiply it by 5. That gives you 20. 20 plus 1 gives you 21. So you should have 21/4. All right. With the improper fractions, you can now just perform fraction addition as you ordinarily would. Here again, you would still use the LCM to find the common denominator. The LCM of 2 and 4 is 4. So we would take the first fraction and we would multiply on the top and the bottom by 2. 2 times 7 gives you 14. 2 times 2 gives you 4. So you'd have 14/4 plus 21/4, and that would give you 4 plus 1 gives you 5. 1 plus 2 gives you 3. So you'd have 35/4. At this point, you would then take your 4, you would divide it into 35. And of course, 4 can go 9 times into 36. So 4 would go 8 times into 35. 4 times 8 gives you, of course, 32. And 35 minus 32 gives you 3 as a remainder. So what we learned here is that we have 8 whole chunks, 3 remaining from how much? From 4. Okay. Either way you decide to add fractions and or subtract fractions, this is totally entirely up to you. Now, with multiplication and division of mixed numbers, though, what we'll see is that multiplication is much trickier, much more tricky than, say, the addition and or subtraction operations. So if you had, say, 3/2 times 5 and 1/4, what's actually happening here is you have the process of 3 and 1/2 multiplied with 5 and 1/4. And essentially, this is going to get really nasty. So what's going to happen here is you have what is known as extended distribution, which we have not talked about, but the extended distribution rule would kick in. And so you would essentially wind up with 3 times 5 plus 3 times 1/4 plus 1/2 times 5, and this would be added with 1/2 times 1/4. And suffice to say, this is a lot of additional operations that we really don't ideally want to perform, and there's certainly a faster way. Now, students might ask me, Mr. B, why in the world are we coming up with all of this nonsense, and where does all of this nonsense come from? Why are you telling me this? Well, recall the distribution law. We learned about the distribution law in week 2 of the course, and we saw that anytime you have a number that's parked out in front of a series of terms that are added together, then what happens is the number will actually multiply across a series of terms. So just to represent this, suppose you had 5 times, we'll give ourselves a good number. We'll do 5 times 4. Okay, we know 5 times 4 should give us 20 at the end of the day, because 5 sets of 4, you'd have 4 plus 4 plus 4 plus 4 plus 4. That would add up to be 20. But here's the deal. If instead you did 5 times 2 plus 2, because 4 is the same thing as 2 plus 2, then at the end of the day, because we said 5 times 4 equals 20, then 5 times 2 plus 2 must also equal 20. Okay, this is what is known as the transitive law. So this would be by the transitive law of algebra, which is to say, anytime you have a situation where you've got one set of properties, say A is equal to B, and you've got another set of properties, B is equal to C, then because A is equal to B and B is equal to C, then this automatically implies that A is equal to C. So in this instance, we have exactly a transitive law case. We said that 5 times 4 was equal to 20. But we also said that because 2 plus 2 is equal to 4, then 5 times the sequence of 2 plus 2 must also equal 20. Ergo, the question is, how can you do a rearrangement to make this follow the distribution law? Well, if you took this number out in front and you multiplied it with 2, and then you took the number out in front and you multiplied it with the second 2, I hope you can see 5 times 2 gives you 10, and 10 plus 10 definitely gives you 20. So everything's all well and good. Okay, well, so what's happening here is you actually have an extension to the distribution law. And so instead of, say, you have 5 times 4, we said that was equal to 20. And then we said 5 times 2 plus 2 was equal to 5 times 2 plus 5 times 2, which we said was equal to 20. Then what happens if I took this 5, and instead of 5, I did something like really strange, like 3 plus 2, and I multiplied it by 2 plus 2? Well, because we already know that 3 plus 2 is equal to 5, and we know that 5 times the sequence 2 plus 2 is equal to 20, since 2 plus 2 itself is equal to 4, and 5 times 4 is equal to 20, then it stands to reason that this sequence of numbers, 3 plus 2 multiplied by 2 plus 2, should also equal to 20. But the question, of course, is, why would that be the case? Or how would that be the case? Well, first of all, you need to closely analyze what's happening here in this second scenario. In the second scenario, we had 5 multiplied with 2, which gave us this first 5 times 2, and then 5 multiplied with 2 again, which gave us the second 2, right? So this whole chunk here would multiply with the first term. So we should have 3 plus 2 times the first term 2. And then we would have the whole first term, which is 3 plus 2, and it would multiply with the second term. And of course, all of this still must equal 20. But the question is, how would it equal 20 exactly? Well, if we do the distribution law on the right-hand side instead of on the left, which we know is possible, You'll have 2 times 3, or 3 times 2, and you'll have 2 times 2 for the first sequence. You'll have 3 times 2 plus 2 times 2 for the second sequence. Now, what's going to happen is you've got to basically multiply your 3 and a 2 together. You get 6. 2 times 2 gives you 4. 3 times 2 gives you 6. 2 times 2 gives you 4. And what do you know? 6 plus 4 is 10. 6 plus 4 is 10. 10 plus 10 does, in fact, equal 20. And so how the extended distribution law works, if we were to put it in terms of, say, a formula, is that anytime you have, say, a plus b, and this is just a sequence of numbers that are all added together in some way, shape, or form, and this is multiplied with c plus d, and this again is a sequence of numbers. And by number, I mean any real numbers. So this could be negative numbers, they could be positive whole numbers, it could be fractions. It doesn't matter as long as we're dealing with whole numbers. Then the rule for what is known as extended distribution, or the special case that we're talking about here, is that you take your first term, a, and you multiply it across the entire sequence of terms that are being added together in this second set of parentheses. Then you take your second term, which is b, and you, of course, multiply it across the entire second set of parentheses. And so you get a times c plus a times d plus b times c plus b times d. And that is going to be what you do. Now, of course, this is all to say that what I'm doing here is the end result of that distribution process. And this would lead us to have a bunch of additional operations that we really would rather avoid. Okay, so it's not that you can't do it, it's just that you should probably avoid doing that because you're likely to make a mistake, all else being equal. And so the question is, well, if we don't do, say, the ordinary multiplication using the rules of algebra because it's too complicated, then what exactly do we do? And it's not that we're not going to use the rules of algebra. It's just that, simply put, it's actually better in this instance if we convert from a mixed number to an improper fraction, and then we just multiply fractions together. And then we'll convert back to a mixed number depending on the problem statement. So what we're going to do here is we're actually just going to convert 3/2 to a improper fraction. So you take 2 times 3, which is 6. 6 plus 1 gives you 7. So you'd have 7/2. And you would multiply that with 4 times 5 is 20. 20 plus 1 gives you 21. And of course, what's interesting about fractions is they always multiply across the top and across the bottom. So 2 times 4 gives you 8. But I better see 21 times 7. 7 times 1 is 7. 7 times 2 is 14. So I got 147 all over 8. Okay. Now, if the question was asking for us to just, have a fraction as an answer or just an answer, 147 over 8 would be perfectly adequate. We don't really need to convert from an improper fraction to a mixed number unless we are, again, it's in doing some sort of engineering calculation where we then need to relay this information to our workers, or the alternative case being where we're asked to do so by the textbook. In this instance, I'd be perfectly okay with you just saying 147 over 8 as part of your answer on the, on a final exam or on an exam in general. But say that they did want you to convert it to an actual mixed number. All you got to do is go one step further. You take 8, you divide it into 147. It goes into 14 one times. 1 times 8 is 8. Subtract. You get 14 minus 8, which gives you, that should be 6. Drop your 7 down. 8 into 67 goes 8 times. 8 times 8 is 64. Subtract 67 minus 64 gives you 3. So what does this mean? This means that you can exactly go 18 whole times into 147, and that you have a 3 as a remainder for a candy bar that has been split 8 ways. And that would be your answer. Now, here's the thing that students are not going to necessarily understand. If you had, or it's not super intuitive, considering that it's not that you can't understand it, but rather it's not super intuitive. It is that when we were doing addition of mixed numbers, you could pretty much just add across the whole terms. But now I hope you can see if you had taken 3 and multiplied by 5, you did not get 18. 3 times 5 gives you 15. And so if all you were doing was looking for a pattern by like multiplying across the whole terms, that is going to be woefully inadequate for this particular situation. And so you should avoid doing that. Instead, definitely in terms of multiplying mixed numbers, this process is always convert to an improper fraction. And then step 2, multiply your fractions, multiply the improper fractions specifically. And then step 3, convert back to a mixed number if need be. But it's not always necessary, okay? If need be doesn't mean you always have to do it. Okay, another example. Suppose you've got -7 and a third times 4 and 5/7, and you're like, what is this equal to? Okay, first and foremost, convert from a mixed number to an improper fraction. So you've got 3 times 7 is 21. 21 plus 1 gives you 22. So this will be 22 over 3, and that is a negative 22 over 3. Wrap your number in parentheses. Then you'll do the same thing for the second improper fraction. So you're going to do 7 times 4 is 28. 28 plus 5 should give us 33. And it is a positive number at this point. And it'll be 33 over 7. Positive and a negative is a negative. So you already know your answer should be negative. You're going to multiply across the top. You'll do 22 times 33. And multiply across the bottom. You'll do 3 times 7. 3 times 7 is 21. And then 22 times 33, I better see people go to the side of their page. I don't want to see calculators being used. 2 times 3 gives you 6. 2 times 3 gives you 6. Drop your 0. 2 times 3 is 6. 2 times 3 is 6. Add everything together. 6 plus 0 is 6. 6 plus 6 is 12. Carry the 1. 1 plus 6 gives you 7. So you've got 726 all over 21. Now, if you did have to convert back to a mixed number, at this point, you're going to go to the side of your page again. You're going to do 21 into 726. This is going to be a little bit long-winded. You're going to have to figure out how many times 21 goes into 72. But considering that 20 goes into 60 3 times, 21 probably goes into 72 at least 3 times. So we'll do 3. 3 times 2 gives you 6. 3 times 1 gives you 3. So 3 times 21 should be 63. You'll subtract. Okay, borrow a 10 from the 7. You got 12 minus 3 gives you 9. 6 minus 6 gives you nothing. So drop your 6 down. Now you're going to do 21 into 96. And that should go 4 times. 4 times 2 gives you 8. 4 times 1 gives you 4. Subtract. And you got 9 minus 8 gives you 1. 6 minus 4 gives you 2. So you've got 12 left over. So what is negative 726 over 21 equal? Well, it equals negative 34 whole pieces. And we've got a 12 remainder out of how many pieces, or how many slices rather, of the pie or of the candy bar? In this instance, we have a candy bar that has been sliced into 21 individual pieces. So our answer would be negative 34 and 12 over 21. One last example. We'll do 2 and 1/4 multiplied by 3 and 1/5. What is this equal to? 4 times 2 gives you 8. 8 plus 1 is 9. So you have 9/4 for your first improper fraction. You would have 5 times 3 is 15. 15 plus 1 is 16. So you'd have 16/5 for your second improper fraction. If you multiply across the bottom, 5 times 4 gives you 20. If we multiply across the top, we're going to have 16 times 9. 9 times 6 is 54. Carry the 5. 9 times 1 is 9. 9 plus 5 gives you 14. So you should have 144 all over 20. Now, if you go to the side of your page, you do 20 into 144, assuming you wanted to, say, convert back to a mixed number. Well, actually, you know what? Before you do that, although that's not really that hard to do, considering that you have an even number on top and an even number on bottom, it would behoove us to perhaps simplify this particular fraction first. So maybe 2 goes into 20 10 times, all right? And then 2 goes into 144. Let's see, 72 times. And then, of course, 72 is the same thing as 36 times 2, I believe. 2 into 7 goes 3 times. 3 times 2 is 6. Subtract, you get 1. Yeah, it's 36. Okay. So 72 over 10 would be the same thing as 36 over 5 if you were to divide the top and the bottom by 2. So 72 divided by 2 gives you 36. 10 divided by 2 gives you 5. And at this point, you can't divide your fraction any further. So if all you wanted was an improper fraction, probably 36 over 5 would be the winner chicken dinner. But you can do a little bit better as a mixed number if you take 5 and, figure out how many times it goes into 36. Well, 5 times 7 gives you 35. So you would have a remainder of 1, which means that if you wanted a mixed number instead of a improper fraction, you would say that you've got 5. And what is your remainder? Your remainder is 1. How many pieces do you have? You have 5 pieces of the candy bar. I'm sorry, I'm sorry, I kind of messed up my interpretation. You should have 7 whole pieces, rather, not 5, but 7, because your remainder, I'm sorry, your whole pieces, 5 goes 7 times into 36. So you have 7 whole pieces with 1 remainder from a pie that has been sliced into pieces of 5. Okay. For the exact same reasons, if you wanted to do, say, the division of mixed numbers, say you did 2 and 1/2 divided by 3 and 1/4, and you were like, what is this equal to? Well, what's actually happening here is you've got 2 plus 1/2 divided by 3 plus 1/4. And it's not to say that you can't actually do this as a fraction. If you wanted to, say, do the division, you would have to do a trick, and that would be to multiply the numerator and denominator by your LCM. In this instance, your LCM of 1/2, or I'm sorry, of 2 and 4, because you look at the denominators here, the LCM of 2 and 4 would be 4. So if you really wanted to attempt this, you would have to multiply the top and the bottom by 4 over 4. And so what's going to happen is on top, you have 4 essentially times 2 plus 1/2, which by the distribution law is going to give you 2 times 4 plus 1/2 times 4. And in your denominator, you also have 3 plus 1/4 times 4. So similarly, you would have to do distribution. You'd have 3 times 4 plus 1/4 times 4. 2 times 4 gives you 8. 4 times 1/2 would be 2. 3 times 4 gives you 12. And 4 times 1/4 would be 1. So you'd have 8 plus 2 is 10 and 13 in your denominator. And that would be your simplified fraction. But This, of course, is rather nasty. Students might ask me, how did I know that I could do, say, multiplying the top and the bottom of my fraction by an LCM? How did I know that that was going to lead to a clean answer? There are all of these mysteries that occur when using this technique. And so for a lot of students, I would beg to say, for the vast majority of students, this technique is simply not taught, although it is, in fact, the way that a Roman would have done division of fractions, because Romans liked to use mixed fractions a lot more than ordinary fractions. And so if we were to do division of mixed fractions and we wanted a much simpler way to do it other than, say, this kind of nonsense that I showed you here, again, we want to convert the mixed number to an improper fraction and then simply use the rules of algebra instead of having to deal with the mixed fractions algebraic form, meaning the 2 1/2 being literally 2 + 1/2, and then 3 1/4 being literally the quantity 3 + 1/4. Instead of dealing with that, if we had just converted these to mixed fraction quantities in the first place, then we can exploit the rules of algebra that we already understand intuitively by this point. And so if I had, say, multiplied 2 by 2, that would give me 4. 4 plus 1 is 5, so I'd have 5/2. Here I'd have 4 times 3, which is 12. 12 plus 1 gives me 13. So I have 13/4. Now, when you have a fraction divided by another fraction, you guys know that you essentially take the bottom fraction, which in this instance is 13/4. You're not going to do anything with the top fraction, but you flip the bottom fraction, right? And of course, you'd have 5 times 4, which is 20. And then 2 times 13 is 26. And of course, you can divide on the top by 2, and you can divide on the bottom by 2, and you get 10/13. I hope I've made a convincing case that either way you want to approach this problem, you will, in fact, get the correct answer. But in my opinion, simplifying this mixed fraction, or rather not simplifying, but converting the mixed fraction to an improper fraction and dealing with that is a lot less time consuming and frankly work/operations that you have to do. Yes, you're going to have to just get comfortable with flipping your fraction and multiplying. You're just going to have to learn that when you divide by fractions, you flip the bottom and you multiply across the top, okay, and the bottom of the fraction. But if you do remember this, then you can do that operation instead of having to memorize a whole new system of techniques in order to manipulate your fraction. All right, so say I had -7/1/4, and I'm dividing it by 2 and 1/5. Okay, what would that be? Well, here again, the literal algebraic form of -7 and 1/4 would be negative symbol, parentheses, 7 plus 1/4 on top. And then you'd have on your denominator, or in your denominator, 2 plus 1/5. If you were going to exploit the technique that I just showed you, you would then calculate the LCM of your two denominators, which in this instance would be 4 and 5, which could give you 20. Go and check that. You will in fact find that 4 times 5 is 20, and 20 is the LCM of 4 and 5. You would then multiply the top by 20, the bottom by 20, or more specifically, you would multiply this nasty looking fraction above by 20/20. You do distribution, you'd have essentially -20 times 7 plus 1/4 on top, and that would give you -20 times 7 plus -20 times 1/4. And then on your bottom, you'd have 20 times 2 plus 1/5. That would give you, in your denominator, 20 times 2 plus 20 times 1/5. And of course, you start simplifying this. So 7 times 2 gives you 114. So 7 times 20 should give you 140. Positive, negatives, and negatives. So on the top, for our top left term, we expect that -20 times 7 gives you -140. And then this would be added with negative and a positive is a negative. 20 times 1 over 4 is the same thing as dividing 20 by 4, which gives you 5. Okay. 20 times 2 gives 40. And then we have 20 times 1 over 5. Sorry. 20 divided by 4. Yeah, 20 divided by 4 gives you 5. 20 divided by 5 gives you 4, rather. Okay. Did in fact do my math correctly there. I was about to be embarrassed. Negative 140 plus negative 5. So if I owe you $140, but then I owe you 5 more, that means I owe you 145. 40 plus 4 gives me 44. And we're at the end of our rope here. Okay. But if instead we had just converted this to an improper fraction first, 7 times 4 gives you 28. 28 plus 1 gives you um, 29. So we would have negative 29 fourths. And this would be divided by 5 times 2 is 10. 10 plus 1 is 11. Then this is the same thing as negative 29 fourths over 11 over 5. And of course, you keep the top term. That doesn't change. But you flip the denominator and you multiply. So you get 4 times 11 giving you 44. Positive and negative is a negative. 5 times 29. So you go over here, you do 5 times 9 is 45. Carry your 4. 5 times 2 is 10 plus 4 gives you 14. So you get negative 145 over 44 yet again. Isn't that awesome? But of course, it is a lot less work than doing this Roman trick of multiplying by an LCM across the numerator and denominator of your mixed fraction expression. Regardless of what way you choose to do, pick a way that makes more sense to you or pick a way that looks cooler to you, however you decide to memorize this technique, and just know that there are multiple ways you can divide mixed numbers. My preference, however, is always to convert to an improper fraction. And then if I'm multiplying, I'll multiply my fractions. If I'm dividing, I will divide my fractions. That's just the way I do it. Students have, of course, their own, they're going to learn in their own way. And so you are free to experiment as long as you are able to obtain the answer and show all your steps. I will accept your work. All right, guys, that's all I've got for you today. Take care.